Next problem, we are going to look at Lenz's law. Lenz's law. So we have a few problems on this. We're starting with number 15. We are given, it's pretty nice, a bar magnet. I think that's the right color. And then we're told that it's going to pass through a coil that is attached to a wire that has a resistor on it. We want to know, if we push it this way to the right, which way is the current going to be going in the resistor? And if we pull it away from the coil, sorry, we're not actually passing through the coil with the magnet. We're just sort of pushing it towards it and pulling it away. And it's going to change the flux of the magnetic field from the magnet through the coil. There's going to be a back, we call it back EMF, but there's going to be an opposing magnetic field, right, which is going to induce a current, and then we want to know which direction the current is pointing. So if we, let's use this, if we push the magnet this way, we're going to be increasing the magnetic flux through the coil. So, to account for the change, there's going to be a B field that is actually pushing in the opposite direction. So we're going to have a B field, a B field that's pushing backwards like this way. Because we're pushing the magnet and we're increasing the flux through the coil, we have a B field that's going to be pushing back towards the left. And if we use our right hand rule, that means that the current is going to be coiling around this way through the coil. It's kind of hard to see that way, but it's going to be coiling this direction through the coil. So what that means is that this is actually going to be going from right to left. So the current goes right to left when we push the magnet towards the coil. Okay, and if we use this same logic, we're pulling the bar magnet away from the coil, right? We're pulling it this way. So now, instead of having this field increase, it's actually going to be decreasing. So let's say they're going to get smaller and smaller. Or really just the value of the flux gets smaller through the coil. Okay, and so to account for that change, then there's going to be a B field pushing in the opposite direction because the change is this way. So now we have a B field pushing towards the right. And again, if we use the right hand rule, it's going to be sending the current the other way. And so it's going to go from left to right through the resistor. So we had a magnetic field that was pushing towards the right, which induced a current that went from left to right through the resistor. Next problem, number 17. We're given a wire with current. It's just standing, it's kind of sitting over a loop of wire. Also, we have a current going upwards this way. And if we use our right hand rule, so that the thumb goes along the wire, it's going to show us that the magnetic field is going to be curling downwards into the page this way and then upwards out of the page this direction on this side. And so we're asked to find the total flux. But since we have it going, it's symmetric, right? So it's going downwards here and it's coming upwards here. It's going to be equal and opposite. That's weird. So the flux is going to be 0 for this case. Again, because it's going down here and it's coming up here. So it just cancels out. Now for the next scenario, let's pull this down. Right, and then we'll take this, put it over here. And so using the right hand rule for this current, it's going to be the same. We have a magnetic field coming down over here, and then it's coming up on this side. So we actually do have a flux. We do have a total flux coming up out of the page. And so what that's going to give us is a B field opposing sorry, that's the wrong way, going back into the page, which means for us that our current is going to be going clockwise because we point our thumb into the page here and curl our fingers around. It gives us a clockwise current. So I is going clockwise using the right hand rule. All right, number 53. We're given two loops. This, and then we're given a wire running through them. If I can move this here, running through them. And then this wire is insulating, right? And we're told that there's a current going around this way on the loop. We're told that the loop is actually traveling towards the right. If I can draw an arrow. And we are asked to find which direction is the current traveling from the induction. Is it going clockwise or counterclockwise? And so we define that we're going to be looking from like straight down the barrel on this side, right? So this one is moving clockwise. And so the magnetic field from here, using the right hand rule, if we curl our fingers around the current, the magnetic field is pushing forward, and then as we move this loop forward, it's going to be increasing through this wire, right? That means that we're going to get a opposing B field coming from the wire, which means if we use our right hand rule again, that we're going to have a current traveling in this direction. And if we're looking straight down, this thing is curling counterclockwise. So the current is going to be we'll just say CCW counterclockwise if we're looking down from the left.